In this video, we will introduce the idea of a tangent line. So what we'd like to do is find the equation of the tangent line to a given curve at some specified point. So first of all, what in the world do we mean by tangent line? So as indicated in the picture down here, the curve we have is in blue, y equals f of x. At the point P, the line which is tangent to the curve would be the line that just touches the curve at that point P, but nowhere else close to P. A familiar way to illustrate this is with a circle, and if you pick a point on the circle, say you want to draw the tangent line there, it would be the line that intersects the circle only at that point. We would say it's the line tangent to the circle at the point P. So if we would like to find the equation of the tangent line, well, the tangent line is simply a line, so the key observation is that we would need a point, which we have. We have the point C comma f of C. So what we really need to find then is the slope. And how we find the slope is through the use of what we will call a secant line. A secant line is a line which passes through two specified points on a curve. So for example, we have the point P and the point Q indicated on our curve. So the line which passes through the point P and Q would be a secant line. And the difficulty of finding the slope of the tangent line is that we only know one point on it. But when it comes to the secant line, we can very easily find its slope. The slope of the secant line, since it is a line going through points CF of C, and we'll go ahead and say that Q is the point that we get when we move H units over to the right. So its coordinates would be given by C plus H, F of C plus H. So the slope of the secant line is going to be rise over run. So f of c plus h minus f of c, the rise, over the run. So c plus h minus c. And notice the c plus h minus c simplifies very nicely. The c over c cancel, and really what we're left with is simply an h in the denominator. Now, the key observation to make is that what we want to do is envision this Q as being a point that we can move. And as we take this point at Q and slide it along the curve towards P, for example, if maybe we stopped here for our new point Q, as we keep drawing these secant lines, the observation is that as the point gets closer to P, this secant line is going to closely approximate that tangent line. That is to say, as we take the limit, this familiar concept that we defined in the previous section, of h going to 0. So h going to 0 makes the point C plus h go to C. The slope of the secant line is going to become the slope of the tangent line. So the key observation to make here is that the slope of the tangent line, the thing that we are looking for, let's call it m, is going to be the limit as h approaches 0 of that quantity f of c plus h minus f of c over h. This is the slope of the tangent line. So once again, from a big picture perspective, the idea is that we've calculated the slope of the secant line through the point P and Q, and then we know that as the point Q slides along the curve and becomes close to P, that is, we let h approach 0, the slope of the secant line approaches the slope of the tangent line, which allows us to define it as this limit. So let's now investigate a few examples. Let's find the equation of the tangent line to the curve y equals x squared at the point 2 comma 4. So in order to find the equation of the tangent line, and I'm going to use TL for tangent line, we need a slope, which we are going to find, and we need a point. And the point that we have is 2 comma 4. And once we find that slope, we can write down the point slope form of a line. Y minus 4 equals the slope we are about to find times x minus 2. So let's go ahead and find the slope of this tangent line. So since it's at the point 2 comma 4, the slope as we've defined it on the previous slide is a limit as h approaches 0 of f of 2 plus h minus f of 2 all divided by h, where in this problem f of x is equal to x squared. So the first thing to do is, since we've written out this slope in terms of a limit of these functions f, we need to get it in terms of we need to do the function evaluations. And I think the easiest way to think of this function evaluation is whatever we plug into the function, so whatever goes in the box on the left goes in the box on the right. So f of 2 plus h, we're plugging a 2 plus h into that box. So 2 plus h squared, and f of 2 is 4. And now this is written out in terms of a familiar problem that we ran across in Chapter 1. So the idea is to, in this case, algebraically expand everything so that we can evaluate the limit. And note at this point we cannot simply plug in h equals 0 because that would make the denominator 0, which is undefined. So algebraically expanding 2 plus h quantity squared. 4 plus 4h plus h squared, and then we have the minus 4. 4 over 4 cancels. Left over in the top are 2 terms. Each of those terms involves an h. So pull that out. Now the h in the top and the bottom cancel. And in terms of h, what we are left with is a polynomial. So we can use this familiar substitution property that tells us to simply plug in the value h equals 0. So 4 plus 0 equals 4. So what we have found is that the slope of the tangent line at the point 2 comma 4 is 4. So substituting that into the point slope form of the line, we have the equation of our line. And if you go ahead and put this in slope-intercept form, which we certainly can, you would have a 4x minus 8 plus 4 on the right. So this simplifies down to y equals 4x minus 4, which will be the equation of the tangent line. So let's find the equation of the tangent line to the curve y equals 1 over x at the point 2 comma 1/2. Alright, so similar to our previous example, for the tangent line, in order to write down its equation, we need a slope and we need a point. We have the point 2 comma 1/2, and once we find the slope, we can plug that into the point slope form of a line to have the equation of our line. So going back to the definition of how we find the slope of the tangent line, it's in terms of the limit as h approaches 0 of f of, and in this case it's at the point 2, so f of 2 plus h minus f of 2 over h, where in this case the f of x is the function 1 over x. So the first thing to do now that we've written this as a limit is to go ahead and take care of the function composition. In terms of our function, we can think whatever we plug into that function, we are going to end up with 1 over that quantity. So if I plug in 2 plus h, f of 2 plus h is going to be 1 over 2 plus h. F of 2 is 1 over 2, and this is all divided by h. And at this point, we need to go back to our Chapter 1 material and just evaluate this resulting limit. Well, I cannot just plug in h equals 0 because that would give us an undefined quantity, so I need to algebraically manipulate or simplify. And the easiest thing I could do is maybe combine those fractions in the numerator into a single fraction. So the single fraction we would have denominator 2 over 2 plus h, where the first fraction is multiplied by 2 over 2, giving you a 2 in the top, and the second fraction is multiplied by 2 plus h over 2 plus h, causing us to subtract from a 2 plus h, and this is all divided by h. So we have to be careful and distribute the minus through to both terms. 2 minus 2 cancels. So in the top we're left with a minus h. And note that when we have a fraction divided by a quantity, we can simply take that quantity and move it up into the denominator of the fraction. So we can write this as the fraction minus h over 2 times 2 plus h over h. The h in the top and the bottom cancel, and what we have left is a rational function, so we can use our substitution property that we've encountered in Chapter 1, and that tells us we can simply plug in that value h equals 0 because the expression is now defined there. And we have a minus 1 in the top, 2 times 2 plus 0 in the bottom, which gives us the desired slope in this case being minus 1/4. So coming back to the right, the slope of our tangent line is minus 1/4, and if we do just a little bit of algebraic simplification, the slope-intercept form is going to become minus 1/4 x plus 1.